All right. So as I announced last week, essentially we have finished learning about all the technical materials underlying this course that is deep learning for natural language processing. Now, today I'm going to talk a bit about what are the limitations or what are the weaknesses of these algorithms that we have learned throughout the semester. Because at the end of the day, one of the most important things as an engineer to know is when your system is going to break down, right? So then you have to do that, you need to know every single, let's say, details about your system, and then those details often have to focus very much on the downside of the system. And then next week, no lecture, no lab session. Thanksgiving week, enjoy your week. After that, we're going to have 2 more lectures, but both of them are going to be guest lectures. One, right after Thanksgiving, is going to be given by my PhD student, Aishwarya, who is going to tell you about the multimodal learning. So obviously, not everything about the word can be learned from text alone. So you'll know that let's say the apples tend to be red, but what does red mean if you don't see the color red? And you're going to read that if you go to, let's say, Niagara Falls, you can actually hear the falls from, let's say, I don't know, several miles away. So what does it mean to hear the fall, right? So all those things actually point to the fact that in order to get the correct, let's say, sense of what each and every objects or each and everything that we observe is, like truly is, we need to be able to see them from multiple perspectives, so via multiple sensor perceptions. And that's what Aishwarya is going to talk about in 2 weeks. And after that, we're going to see how all these algorithms that you have learned throughout the semester can be used for the domain that is not natural language. And that's going to be given by Kunu, who is a research scientist at ByteDance. And he's going to tell you all about how to use all these algorithms for music. And it's quite fascinating how every single algorithm that you have learned can be used as they are for doing music recommendation, music generation, music recognition, and all the things that you can imagine. But those are all the kind of, let's say, rosy picture. Today we're going to look at slightly less rosy picture, or pretty, the desperate picture of deep learning. And then in particular, we're going to talk about the 3 issues. Of course, they are all somewhat related to each other. The 3 issues that we don't know how to solve with our algorithms or the technology. And then they are non-identifiability, spurious correlations, and feedback loops. It's going to be a bit of a mix of the technical content and non-technical content, but we're going to go actually quite deep into the technical content, because it's not a lecture that I give to undergrads. We're all master's students, PhD students. So the weirdest thing is that all these deep neural networks can work really well when you look at the average accuracy. And then in the case of the language modeling, what we looked at was the perplexity. And what was the perplexity? Perplexity is really just an exponentiated average loss. So, when we look at the kind of average accuracy, we can easily get a bit of a sense that the ill perception that our models are doing amazingly well. But then what people have realized, for some time already, like since like 2012, 13, 14, is that these models can actually solve problems in a way that we don't want it to solve. For instance, let's look at this particular example of pneumonia recognition, which has become extremely important problem due to the COVID-19 and all these, the pandemic. Now, what we want is that we want our system to look at the lung, right? Lung and the surrounding area to figure out whether there's the subject is going through or the patient is suffering from pneumonia or not. But then the weird thing is that once you train a model on a data coming out of one hospital, and then you see that on the test set or the validation set from the same hospital, the system works really well. And then you use that system for another hospital, the system completely fails to recognize pneumonia. And then, like obviously what you can do is you can look into what kind of, let's say, features or what kind of input words, right, or pixels that the model particularly focuses on in order to make a prediction. Now, what you notice is that these models are going to look at very different, the parts that have nothing to do with the lungs. They often look at the actual markers on the X-rays. They're going to look at the, let's say, some particular like shape of the body. And then what you notice is that those are all those artifacts that arise from a particular hospital's practice in how to take the X-ray. And that's precisely what we want the model to do. We want the model to look at the lung and then tell us whether the patient is suffering from pneumonia or not. So why does that happen? Why does it happen? Let's say I did do some thought experiment. So I went to Google image search and then searched for birds, images of birds. And then let's say I got these 4 images. And then our goal is to, by looking at these 4 images, trying to figure out what are the good features by which we can build a classifier that's going to tell us whether there's a bird or not in an. Now, looking at this, I can imagine that there's 2 different ways in which 2 different ways to build a classifier. One is to actually look at a beak, right? If there is a beak in an image, there is a bird. What would be another one? Another one is that just looking at these 4 images, if there's a branch, then there is a bird. Now, obviously, if you wanted to build a bird detector, the first one is much better solution than the second one. However, looking at these 4 examples alone, without talking too much about whether we are doing a bird detection or just trying to say, okay, these are the positive examples, and then there will be 4 different images that are negative examples, then both of them are equally likely, equally desirable. Now, one might say that, that's just a problem of overfitting, but that's actually not true. So using the same query, I got all these bird images from Google image search, and then I'm going to look at much more than what we looked at. These 4 images are the ones that we looked at, but now we're going to look at much more of them. So what you notice that both classifiers, one that looks at a beak, or that looks for a beak, and then the other that looks for a branch, both of them are equally well working, even on these held out examples. So it's not really an overfitting issue. And then just having a validation set is not going to necessarily save us from this issue. So then what is happening here? It turned out that this actually is not just a kind of, let's say, toy thought experiment, but it actually does happen quite often in reality as well. So this is a study from 2 years ago, done by Emily Denton and others from Google. Emily used to be a PhD student here. She graduated, she joined Google. She's still at Google, if I recall correctly. And then what Emily wanted to check was, well, there are those so-called smile detectors. And those smile detectors are used like really every day. Whenever you have a phone taken out, trying to take a picture of others, nowadays the latest phones all have the smile detector, and then they actually focus more on the person in the scene. The smile detectors are used in many different places. But then you might think, okay, so what are the things that these classifiers or these smile detectors look in order to determine whether a person is smiling or not? From our perspective, what is the desired way to tell whether the person is smiling or not? We'll look at like the lips, right? We're going to look at a bit of eye, and then you have to see if the person is actually smiling, right? That's what we would think. But then the smile detectors that they have trained and tested turned out to capture all those weird, spurious patterns. It said that, okay, if a person has a higher cheekbone, then detector was more likely to say that person is smiling, less smiling, or I forgot the direction. And then if the person has a bigger nose, then the chance of smiling was lower. That's not really an idea what smile detector should do, right? Or what the detector was doing is that if the person looks younger, the person is more likely to smile. Unlike yes, old people tend to be grumpier, but that is not what smile detector should do. So this is effectively working as an age detection, age detector predictor. This is working as a big nose detector. This is working as a higher cheekbone detector. And none of them is supposed to be a small detector, but those turned out to be what our classifiers are relying on, or their classifier was relying on. A similar thing happened in the study from, again, 2 years ago. This one coming out of the, that came out of the Facebook data research, where they did was to look at the off-the-shelf object recognition systems. So you go to Amazon AWS, there's an AWS Vision. You can use the service and then upload a picture, and it's going to detect every object you can imagine for. There's Microsoft Azure, so there's Azure Vision API, you can use it. Google Cloud Vision API, you can use it. There are a few more that you can use. There's a Clarify, which was founded out of NYU. And then all these companies provide this off-the-shelf, pay-to-use vision services, object detection services. So what they did was they did test all those systems, off-the-shelf commercial systems, using images that come out of the diverse set of countries. And then one of the weirdest things that they have noticed was that the accuracy of those classifiers, in fact, correlated with the average income or the per capita income of the country from which the pictures were taken. That sounds a bit weird, right? Why would a object detector works better in US than in, let's say, Sudan? There's no reason that should happen. So for instance, if I were in Sudan, I'll be able to tell whether that's a chair or not, regardless of whether I'm in Sudan or in US. But somehow our classifier is not like that. And then the difference is quite dramatic. The accuracy goes from 70% for a country where the monthly average income is $55, all the way to 90% for a country where the monthly average income is more than $10,000. Yeah, you might be wondering what country that is. That must be Luxembourg, if I recall correctly. But anyway, so there are countries like that. And then if you happen to be born in that country, then somehow all these cloud services are going to work better for you. And that's a bit weird. So what they noticed was that there was some issue with the data that was used. I mean, they didn't actually explain the whole thing, but some part was that all these systems tend to use the ImageNet or the data set they collect based on the procedure by which the ImageNet data set, which is one of the most widely used data set, was created. And then most of the images end up coming out of North America, Europe, or some part of East Asia. On the other hand, when you look at the word population, it's almost like inverted image, except for Europe. So the population-wise, South Asia, East Asia, and then Africa actually take up let's say, most of in fact, majority of the world population. But when you look at the ImageNet or where the images come from, that doesn't really represent where people live. It turned out that actually does result in this kind of discrepancy. Then, it turned out that there are more images in ImageNet coming out of the richer countries. Okay, so not that great, although this turned out to not explain the whole thing. So we're going to get to why this happens even further. And this is what I wanted to say, is that it's not only the data. A lot of people make a mistake saying that, well, we just collect better data. But then the thing is, even if we collect the better data, unless the data is perfect, and even if we collected the perfect data, our algorithms turned out to be not that great at the moment. Our algorithm has a lot of issues. What is the issue? Is that our algorithm doesn't know what are missing from the data. So even if we collect the perfect data, there will always be something that are missing. Why are there going to be something that are missing? If you collect the data so that there's nothing missing, that's called universe. We can't really collect the data that has everything observed. It's just impossible. And then, furthermore, because of the kind of, let's say, unobserved variables in the data that is inevitable, cannot really be avoided. What happens is that, and then on top of that, we end up with the cases where we can get multiple possible perfect solutions, just like the one that we looked at. For a detector, we could get 2 perfect solutions, right? And then it turned out that there are infinitely many possible solutions in these deep neural networks. And then the intended solution, or the solution that we really want to find, turned out to occupy a tiny fraction of this space of all possible solutions. And there are many different, let's say, ways in which we can characterize these solutions. Well, looking at this plot doesn't really tell you too much, so we're going to look at a very particular example here. So this is a study from Weber and others from 2018. So this was done at the Stony Brook. And what they did was they created 4 different types of test sets. So they created a training set first, and then they took out, let's say, a small portion and then call it a test set. And then they call it a standard test set. But they created 3 different test sets that have slightly different properties. So it was related to the sequence modeling. So we know how to do that. On one test set had more repetition, slightly more repetition than usual in every sequence. One test set was generally shorter than the training set sequences. And then the third one had generally longer sequences. Now, if you only look at the standard column, when they train 6 different models, they're essentially the same. They all get 100%, near 100% accuracy. However, when you look at, let's say, the repeat column, what you see is that the second solution is somehow doing so much worse than all the others. Oh, but then let's just look at the final column and the second solution. Second solution is actually doing amazingly well on these longer sequences, while all the other systems are completely failing. And let's look at the third solution that is actually getting essentially 0% accuracy on this long sequence test set. And then let's go back to the repeat. It actually got the sequences with more repetitions perfect. And then similar thing happens with the short sequences as well. The final model that works really well in short sequences or miserably fails on longer sequences. But this is a big issue because in this particular case, because they synthetically created these data sets, they could tell what happens and could distinguish all these solutions. But often, what we do is we only have this standard. And then by looking at this standard test set, we can't really tell the difference between all these 6 models when they are in fact very. So how can we actually address this issue? So we got tons of different solutions, and then all those solutions turned out to be quite different from each other. And then one way to address that is to use all of them. We're going to use all possible solutions that we get out of neural net training. And then one way to do so, there are many different ways to do that. One way to do so is to rely on the idea of the Bayesian machine learning. We did touch very briefly upon it as part of the probabilistic modeling, but we'll go through it once more here. So we need 3 different distributions. As you recall, we have a likelihood that is, and then here, the parameters. So the parameters of our model are the random variables that are not observed. So if you recall from the probabilistic principle component lecture, we had the z, the unobserved hidden variable, and then we had x, that was our observation. Now in Bayesian machine learning, we have the exactly same thing, but our unobserved hidden variable is theta, the parameter of our network. And then given that theta, we have the variable d, that is the one that we observe. And then that's the data. And then what is the idea here is that if the data was generated from our model, given its parameter, so then we have a likelihood. And then likelihood is going to be a exponentiated negative loss, or the exponentiated, yes. So this is loss. So it's going to be the exponentiated negative average loss on the data set. What is this? This is perplexity essentially, right? So what we are saying is that the likelihood is going to be the inverse of the perplexity, in the sense that so if our model is making a good prediction that is at a very low loss, then the probability is going to be assigned high on this data. So that's the likelihood. So this condition. What do we need more? We need a prior. So what is a prior on these parameters? So parameters are our hidden variables, so we need a prior. And at the often we can use some kind of Gaussian prior or whatever the prior that you want to impose. But as we talked about, priors don't really play too much of a role in our setup because of the size of this data set is really, really large. Once we have this setup, now by having this particular format, if you imagine the log joint probability of theta and theta, that just becomes the usual loss function plus the regularization. That's how you actually make the connection between Bayesian machine learning and usual machine learning that we have learned. And given that, what do we do? So what we did earlier was to use the stochastic gradient descent to find theta that's going to maximize the log probability of this data, or maximizing the log probability of the theta, this parameter given the data. But that's not what we're going to do. In Bayesian machine learning, what we're going to do is we're going to consider all possible parameters. So for every possible parameter configuration of a neural network, we know how likely that is, given that we have observed this training data. That's what we know. That's the posterior distribution, right? Posterior probability. And then using that, and then that's going to be the weight that we assign to one particular configuration. So we have infinitely many possible neural nets, right? Because the parameters are all real values. We're going to try each and every one of them, and then we're going to consider the one that has a high posterior probability, given our training data, more so than other configurations. And then we compute the expected prediction we get given the new input x. And that's how we're going to do the Bayesian machine learning, and then that's called the predictive distribution. So we get the probability of the target, probability distribution over the target, given the new input and the data. Now there's no theta here because we're going to consider all of them and then marginalize them. Unfortunately, this is a great idea in a sense that this can happen. So you can imagine that the x is going to be just all possible classifiers you can imagine. We're going to compute this posterior distribution, posterior probability for each one of them. And then in the limit where we're going to push this further, we essentially want to consider this solution, this solution, this solution, this solution, 4 solutions, and then average their predictions. That's what we do. Except that it's really difficult to compute this. It's extremely difficult. So how do we get all those different solutions and then figure out what are the reasonable solutions and how do we actually get all of them? Turned out to be extremely difficult. But then the nice thing is, it turned out that we can just get them by training a lot of models. And that's the idea behind building an ensemble of neural networks. We're going to train a model multiple times, starting from different random initialization, and we end up with the different solutions. Now, that's a kind of the same long story that we did another, let's say, 2 weeks of lectures, but we can get a bunch of different neural networks by just training them multiple times. And then once we do that, we can simply average their prediction. Not the parameters, but the prediction. And then that actually does remove a lot of the idiosyncrasies coming out of the individual models. And unfortunately, it turned out that it's really nice, but not perfect. It's nice in a sense that we are not going to have a crazy, let's say, solution that comes out of in one model, because 2 models are going to cancel each other on those crazy cases. However, and then having more and more so always helps, except that there are things that cannot be removed by having many different models. Let's see what those are. Before that, what is really the key point here is that it's really difficult to tell whether your classifier works well or not. That's actually the key point here. Because what we've talked about so far is that we've been talking about how to do the validation. So we're going to set aside some of the examples, not using them during training, and then relying on how well my classifier is going to work on this held out set. But what we just saw was that that's not really the whole story. Because even though many different classifiers may have the same level of accuracy on this held out test set, that doesn't mean that all those classifiers are solving the problem in the way, in the same way. They might solve the problem in 2 different ways. Some of them are going to look at the beak of a bird. Some of them are going to look at a branch. Some of them are look at the wings. Some of them are look at the sky. But on most of test examples, they're going to make the same prediction and get a similar level of accuracy. And then in order to avoid that to a certain degree, we can use as many classifiers as we can. We're going to train many classifiers, and we're going to get the consensus from those multiple classifiers. And then our hope is that that's going to save us from this idiosyncrasies of those individual classifiers. It turned out that that's not really enough. That's not really enough. So why is it not enough? Now, this is where the limitation of our own statistical approach comes in, is that because we can't observe the world perfectly. We cannot observe the world perfectly. It's just impossible. We often try to solve a problem where the goal is to try to figure out, given the input, what the output is. So we're trying to figure that kind of, let's say, influence of the input on the output, or as we talked about, the arrow can be flipped very easily, or how the choice of the input has given rise to the observation. So the X could be the picture of a bird, and Y could be a label that is set to bird. You know, we can go in either direction. But what is issue is that what is the issue at hand is that we often have these unobserved confounders that affect both the input and the output. And those can be anything, and we actually don't know often what those confounders are to start with. Not to mention that we often cannot observe them, even if we know what those confounders are. And then this existence of the unobserved confounders that influences both the input and output creates so-called backdoor path, or the hidden path of the correlation between X and Y. So there is a direct way in which X can cause Y. But then because of this hidden confounder in the middle that we don't observe, there will be a correlation that is created indirectly via this confounder between X and Y. Now our goal obviously is to to focus on this direct correlation. But it turned out that we can't really do that. The mathematics turned out to tell us that it's kind of impossible. So what are some examples? Let's think about it. So if I look at a picture of a bird, and then in that picture there is a bird. Now I can imagine that the hidden confound, so I can imagine that the X is an image of a bird, Y is whether there is a bird or not, so that's a class. And then you can think of Z as the location where the picture was taken. Now, if the picture was taken in the forest, the chance that there are going to be birds on the image goes up. Generally, it goes up. But at the same time, what happens? The chance that the branches are in the image also goes up. So what that means is that by knowing that the picture is being taken, so the scene is we are in the forest, gives the X to have more likely to have both bird and a branch, and also makes the Y to be more likely to have a bird in a picture. So that that location can be a confounder. Now, sad thing is that as you can imagine, by simply looking at an image, we often don't know where those images were taken. Sometimes we can know, but we only get a very noisy metadata address, and we don't really know where the picture taking took place all here. So that can be considered as an unobserved confounder. And then because of that confounder location, this having a branch in an image becomes a very good indicator that there is a bird in the picture. And then that is how the correlation does not imply causality actually comes in. Is that the X being in the image having a bird, and then so the image having a bird in it, and then whether bird is in the image, so the indicator, these two are correlated, should be correlated because there is a bird in an image. However, because of the Z, now there is a spurious correlation that appears between whether there is a bird and then the branch being in an image. And then that's when we say that, okay, there is a correlation which doesn't imply the causality. the branch does not cause whether the bird exists in an image or not, but there is a correlation between branch and whether there is a bird. Now, it turned out that it's actually impossible to tease these two apart purely based on the observations of X and Y. So if we don't know what this is, then we don't observe it. We only get these static observations. So people just dumping a bunch of images of birds and the numbers with the labels and me, and then I can take a picture myself, then it turned out that I cannot really distinguish between these two. And then some might actually say that, well, based on what we have learned about all these graphical models and probabilities, can we just compute P of Y given X by simply marginalize out the C? Because we can estimate C, that we can sometimes do that. But it turned out that this quantity does not equate the quantity where we are going to remove the bird from an image, like somehow, and then see how the label Y changes. They turned out to differ from each other in general case. There are some special cases that they do equate each other, but often that is not the case. So what can we do? What can we do? So this is where the machine learning or the statistical machine learning, more precisely, is causality. So one thing that we can in fact do is to intervene directly. So what we're going to do is that instead of using only the static observed data alone, we're going to say that we're going to be very active and then say that what if I change the image directly myself? I'm going to just remove all the birds from the picture. Then how the Y change? If the Y changes so that branches are left here, but I only remove the birds, and it turned out that Y stays same, then I know that the birds are the ones that matter. If I remove the branch and then look at how the Y changes and the Y doesn't change because the bird still is there, then I know that the branch shouldn't matter. And this is the idea behind the randomized controlled trial. Now everyone has become an expert in randomized controlled trial thanks to the COVID-19 vaccines and so on. But the reason why, so the exactly same thing. X is whether you get vaccinated or not. Y is whether you build up a protection against COVID-19 or not. By just looking at the observations, so static observations, we cannot really tell whether vaccination is indeed increasing the level of protection against COVID-19. However, so what we do is that we're going to randomly assign people. So we're going to actively intervene on X. So what does this active intervention gives us? Is that the active intervention is going to break this influence of the unobserved compounder. So what would be such an unobserved compounder? In the case of the vaccination, it can be the income level, availability of the clinics, or the historical reasons as well. Some of the community suffers from the malpractice of medical malpractices in the past, and then they might actually make people less interested in getting the vaccination and whatnot. And then which of those factors might be compounders? That is that they influence the outcome. So the protection against COVID-19. Now it turned out that actually makes sense, right? So lower income level tends to imply that the hygiene level of the community tends to be lower. The hygiene standard is going to be lower. That actually does often lead to a higher degree of transmission of infectious disease. So those things are going to be the compounding factor. So what they do is to cut out this influence by saying that if we're going to spend tons of money and investment by assigning randomly who's going to get a vaccine, who's not going to get a vaccine. And then in fact, because knowing whether one is getting a vaccine can also influence the level of protection against the COVID-19, because some people who knows that I got a vaccine, so I'm going to just go to a club without mask or so on, just because I got a vaccine. And some other people might say, oh, I wasn't vaccinated, so I'm going to stay at home more so than before. So what we have to do is some of the perception can also serve as a compounder. So we have to be triple blind. So the subject doesn't know whether they were vaccinated or not. So that's why we have placebo. So you get essentially just a water in this case, saline water. Doctors don't know, because doctors might actually, express some, let's say, or give some cue to the patient or the subject that they were vaccinated. So doctors don't know. And then the people who collect the data also don't know. Only afterward they actually collect it, review it. But the all results is going to be reviewed by an independent panel. But as you can see, it's a bit difficult. This is not easy. Vaccinated or not, one dimension. We can try to get as many subjects as possible, and then try to balance the, let's say, vaccinated and unvaccinated as much as we want. But what if X was 1,000 dimensions? The number of participants we need, or the number of the participants we need for each configuration has to be non-zero. It has to be greater than 0. If we have 1,000 possible combinations, so binary, let's say vaccinated or not, vaccine A or not, vaccine B or not, vaccine C or not, and then let's say we have 1,000, so 2 to the power of 1,000 possible combinations. That's way over the entire population of humanity, entire humanity. So it doesn't really help. We can't really, so this kind of randomized controlled trial turned out to be really, really difficult to use in cases where we have more than few dimensions of X. So what can we do? But the funny thing is that in the case of bird detector, we somehow knew. We knew that the classifier that's going to look at a branch is an incorrect classifier. How did we know? How did we know? I actually don't know how we knew, but we knew. That's the one thing we know, right? So then the idea is that what if we used us together with the machine learning algorithm so as to train a model to be less susceptible to these backdoor path or the spurious correlations. So we're kind of, let's say, flipping the table. We've been talking a lot about how to automate or how to build this kind of automatic algorithms to serve us. But now we're going to talk about how we can serve machine learning algorithm so that it's going to do better for us in the future. And then this is the idea of the so-called human and model in the loop, or human in the loop, or the left in the loop system, where the idea is that because humans turned out to be an amazing machine at figuring out all these spurious correlations and figuring out whether a classifier is relying on spurious correlation, we are going to have a machine being tested or challenged by humans. And of course, it can be this really individual person, or it can be some expert who's going to come up with the rules that are going to be used to challenge this model. And then whenever the model fails a challenge created by a human, then that failed example becomes a part of new training example. And then those new training examples are the ones where the spurious correlations that were being used by the classifier are not valid anymore. So then, having those examples in the data set will force or encourage the classifier to avoid relying on the particular spurious correlation that made it fail the challenge by the human. And it turned out that this approach has been quite powerful in the sense that the people could show that, we can actually have the Amazon mechanical Turk and ask the human Turkers to just create all those so-called adversarial examples, or the examples that do not exhibit a same kind of spurious correlations that were exhibited by the entire training set. Now, whether these can be used well for training the next generation of models is still a question that is being actively sought after. But this kind of system, this kind of, let's say, framework, or human and model in the loop framework, allows us to figure out these spurious correlations that are being exploited by our models. Unfortunately, this turned out to be problematic. This whole framework is super problematic because, first of all, it gets more and more, increasingly more difficult. As you go through these rounds, the model gets better and better, and then we start actually failing at figuring out those spurious correlations. Because spurious correlations don't have to be that obvious. They can be very complicated, and at some point, we fail to find them. And then if you notice, we had to create this graphical model, right? So we have Z, X, and Y, and then we have to decide on the directions. How do we actually know that those arrows are correctly placed? How do we know that their directions are correct? It turned out that different assumptions lead to different optimal setups for this kind of human and machine in the loop systems. And then often we have to test a few of them to see which one makes more sense. And then that becomes increasingly more difficult as the system gets more and more complicated. But this is the difficulty in doing academic research, but in reality it's even worse. This kind of human and machine or the automated algorithm in the loop has been used ever since, let's say, the beginning of the internet era. So if you look at Facebook, I don't know if anybody uses Facebook in your age group anymore. I heard that I don't even use it that much anymore. So. But Facebook is not even arguably, it is actually the most widely used social media in the world at the moment. And then you have I don't know if you noticed, so that when I say Facebook, it includes Instagram as well. I don't know if you noticed, but you don't get to see all those, let's say, crazy hate speech or whatnot on Facebook or Instagram that much, compared to how much is being posted. The actual amount of the hate speeches or the political speeches or the very the really violence inducing speeches or the posts that are being made to Instagram, Facebook, Twitter, and so on is so much more than what we see as ordinary users. And then the reason why we don't see them are twofold. One is that they actually do use machine learning quite heavily to detect automatically whether the new post is, let's say, inducing violence or inducing hate. And it actually works pretty well. Like it gets a 90-something% accuracy. It actually works pretty well. Now, the people who post all those things are also evolving, so their strategy is becoming more and more sophisticated. So the accuracy cannot really go up that easily. It often comes down, they get better, comes down, they get better. It works well. But then the thing is, 90% of about 1 billion posts a day seems really large, but there are still 10% of, let's say, hundreds of millions of posts that are still being spread out through the system. So what do? They actually do have the humans, people working 8 hours a day, 5 days a week, sitting in front of the laptop or the computer, just looking at all those speeches that have been deemed hateful, reported by the users or reported by machine learning algorithms. Read it over and over. And then they actually do have a center in Arizona. Now, Facebook doesn't hire them directly. Apparently, they work with obviously one of those big consulting firms. So they are the ones who are hiring them. So and then most of the people work there for only about 2-3 years, because after which they actually get depression, clinical depression, then can't really work there anymore. So one of the big things that they made changes last 3-4 years, I heard, is that they started to hire therapists in the whole, let's say, center as well, so that anybody can go talk to the therapist directly. But it turned out that we can help the humans to help machines. And because of these people, the hate speech detection system gets better and better, because we get better labels and the better examples that the spurious correlation does not apply from the previous data set, but the people actually get hurt. And then that actually does happen quite a bit. So this kind of, let's throw the system model in the wild. We're going to just deploy the model, and then let's see how well it does. And then whenever it fails, we're going to collect more data. But that actually is a bit problematic. So this is one example from Zoom early last year, 2020. People suddenly started to use Zoom so much more. And then indeed, people started to notice some issue. So for instance, the Black people just used to disappear from Zoom because of the background. They just really literally disappear. And then, of course, because of this, Zoom it doesn't happen anymore. But that means that essentially quite a large portion of the world's population just never appeared on Zoom for about a month to 3 months. Okay? And then another example is this. I don't know if you can notice this. By the way, this hasn't been proven. I mean, it's still debatable. Whenever Twitter or some of the websites so let's say you write an article, you post it on your blog, and then let's say you take the URL and then share it on your social media, and then let's say it had some pictures in the blog. Have you ever thought how the social media web pages are choosing which thumbnail to use? It actually does it automatically, so there's a lot of machine learning going on. And then those convolutional networks are going to look at each of the image and trying to predict whether which image is going to is most salient. And then using that, they choose the image, and then given that image, of course, images tends to be large. So they also use some automated algorithm to create a thumbnail. And then how you get the weight area to crop out is also often determined by convolutional network, so as to maximize the either engagement or the click-through rate or not. And then the Anima, the professor at Caltech, and who is also a research director at NVIDIA, she at some point noticed that this is really weird. All the machine learning scientists who are male, Twitter always crop out the face. But for the woman, Twitter always crop out the torso only. Wonder why. This was really weird. So it's been not proven, but there are so many examples like that, right? And then you think about it. Why is that? What is that difference, right? There is some hidden compounder, and then in this particular case, the hidden compounder is the gender, and then the gender is going to affect other things like what kind of users are doing based on the pictures they see, and then that is influencing both the actual image of the person, and also the area that cropping, the particular area that needs to be cropped in order to increase the click-through rate. I'm going to let you actually have imagine about why that would happen. But essentially, what this means is that because we are working at a so larger scale nowadays, you make one system, you deploy it out there. If you work at Google, Facebook, number of the users of your system is effectively in billions. And what that means is that to collect some negative examples, you might actually negatively impact quite a huge population overnight. And then sometimes that kind of damages can be irreversible. Now we're talking about the thumbnail generation, so we feel like, oh, that's okay, we'll fix it. Twitter took about half a year to fix it. Zoom took about 3 months to fix it. But then there are actually few things that fixing is a bit difficult. And this is one example where I was stunned. And is that can machine translation be dangerous? It's unlikely. But then it turned out that the Facebook's machine translation system made a mistake of translating the good morning in Arabic, which was kind of transliteration in Arabic back then, into attack them in Hebrew. And then the person was actually visited by the Israeli police. And then if you live in a Palestinian place, if you're a Palestinian man, and then if you get visited by Israeli police, that's not really a good sign, good thing. That's a very traumatic thing. And then this is just because the machine translation system made a mistake. And if you think about how many posts on Facebook are automatically translated by these machine translation systems, you cannot really, you start imagining that this kind of thing is happening. And then even this kind of this innocent machine translation say, well, at least supposedly innocent machine translation system can be hurtful for some populations. Then that actually happens over and over. And this is not natural language processing, but for the computer vision algorithm that takes as the input an image from a surveillance video, and then the algorithm is allegedly predicts whether the person should be is actually one of the people with the outstanding warrants or not automatically. And then it actually made a mistake in 2020 last year. And then that person who was mistaken by this algorithm, that police actually didn't know how it worked, by the way, because these companies, private companies supplying these algorithms to the law enforcement, they actually don't reveal the actual algorithm that is being used and then the actual logic behind those algorithms. And then they just arrested the guy from the guy's the house in the lawn, and they detained for 48 hours because you cannot actually, so police can, with a reasonable, the suspicion, they can detain them, anyone for like 48 hours or so without having any access to the phone calls or whatnot. And then this kind of thing happened, and then he actually had to pay $1,000 bond in order to get out, which is really weird, right? So then these are really the things that happens quite over and over. By the way, this is a very really nice book, Automating Inequality by the Virginia Eubanks, and then this thing actually happens. It happens like so many times, this kind of automation, and then we try to solve it by having humans, right? So this is one example where they introduced in Indiana the automated eligibility system for the, what was it, the food support, I think? Yeah, I think so. But then there, of course, it's not just the automation only. There's always a people who are going to be able to give you the tech support or the legal support or whatnot. But then, even then, and then the system has been improving. But then during that time, about 5 years, a lot of people actually lost the legitimate, let's say, support that they were getting from the state. And then, of course, the only thing, and then they actually did really significantly affected the people in poverty. So the people who don't want to actually hurt. Like, yes.
I mean, eligibility. Does that mean like these algorithms are running on like the information about the families and stuff, and then just like?
Yep. So should they
yeah.
are they eligible for state benefits, right? Or something like that? And
then people who are applying.
Yeah, so people who were applying back then and who were actually already receiving benefits, they were all, let's say, screened again by this automated system that was supplied to Indiana State by IBM back then. And then that actually caused a huge, let's say, disruption in the whole, let's say, benefits program in Indiana. And then that, of course, affected only the people who needed those benefits, right? Who needed them. So often these systematic failures tend to affect the people who are indeed disadvantaged in the society. And then these things are often irreversible. You can't really reverse 5 years of lack of, let's say, medical care, the food support or whatnot overnight. It doesn't work like that. Now, the funny thing is in 2014, Indiana's, let's say, the governor was touting that the system really works because they were able to drop the number of people who are relying on the state, let's say, support by 8%. Well, obviously, if the system doesn't work, then the system is going to say, oh, we don't need to support anybody. And the number of people who rely on the state support drops. Yeah, so then that's the kind of classical way of misreading this kind of outcome or the accuracies of these automated systems. And then that's why we've been focusing a lot on evaluation. In fact, last week at the lab session, 2 weeks ago, last week at the lab session. So then we should do much better, right? So we can't really just deploy it and hope that things are going to work well. But then what can we do? If we draw those causal graphs, then we can be much more careful about it. Because just like the vaccination, right? So the testing the efficacy of the vaccination, we draw the causal graph carefully. Then we decided where we're going to intervene. And then we ran the randomized control trial and then drew a conclusion that it is hugely effective. We're able to do that, we can do that. But that seems a bit difficult in reality because there are going to be thousands of variables, not just one binary variable. Let's say, let's go back to the bird detection example. What are the input variables? What was X? X was an image. And then if you think about this, the 4K, 8K, like the TVs these days, and then you take a single frame, it has millions, if not hundreds of millions or billions of pixels. They are highly correlated and so on. How are you going to do the randomized control trial on the billion pixels input dimensions? We really can't do that, unfortunately. We really cannot do that. So then, can we do anything? Maybe there are some easier way to get around it with some limited, let's say, degree of success. So one thing you notice is that there are two classifiers that we mentioned about the bird detection earlier. They were equally good on the images that you get from the Google image search where you type the birds, right? But then if you search for images of the birds in a slightly different way so that you get the images of the birds from the indoors, then you notice that there aren't any branches except for one image. So the branch detector in this particular case is going to dramatically fail. On the other hand, the big detector still works as well as before. So what does it tell us is that one way to think about these robust or the causally, let's say, reasonable classifiers are the ones that are going to work regardless of where or in what kind of environments we use that classifier. The bird detector should work when we use the bird detector in a forest, or when we use it inside in your house, or some kind of zoo. Right? If the bird detector only works when we use it in the forest, that's more or less the forest detector rather than a bird detector. And then this is the idea behind so-called invariant prediction principle. Is that our prediction needs to be invariant to the changes of the surrounding environment. And then what does that mean is that the Z, the unobserved confounder, is essentially the thing that is determined by the surrounding environment. So cutting out this connection is equivalent to being able to estimate the relationship between the input and output that's going to hold regardless of where you are. And then this is a nice way to think about what is the right kind of, let's say, algorithm to make, or how you evaluate your system, or at least imagine what's the right or the wrong about your system. Because you always imagine, or you always try to make a mental transport of your algorithm classifier either to the future or to the past, and then see if that still works. So what would be such an example? So one example I often go to these days is that it's a bit crazy, but generally trying to tell whether any individual, whichever country you're talking about, any individual is eligible for voting is not that trivial. It's very difficult. There are a lot of, let's say, legal causes that you need to consider. In some countries, let's say, convicts cannot vote. In some other countries, convicts can after, let's say, a few years. In some countries, you have to be over 18 to vote. In some countries, you have to be over 21 to vote. In some countries, you have to have a certain, let's say, degree in order to go on to become a candidate. It's pretty complicated. And in US, it actually also depends on the state as well. So it becomes heavily complicated. But then let's say you build a system that's going to determine the eligibility as a voter eligibility picture. And it's going to look at the entire, let's say, feature of the person and the law in order to make a determination. And then imagine that you build a system that works perfectly in 1950s. And then you're trying to bring it to 21st century and then use it. Would it work well? If not, why wouldn't it work well? Now, one thing I can tell you is that the system that you built probably is not going to work well on about half of the population, because it's going to say that the female, nope, no voting right yet in about 25 states or so by then. So but now it doesn't really matter if you're a female, who cares? You are eligible for voting, right? But it wasn't the case back then. So this is a really way to think about it. So here as well, if I made a bird detector, and then if I've been using it near the forest only, and then if I imagine that I'm going to use the same detector in, let's say, urban area like in New York City or whatnot, will it work well? And then what we want is that we want to find a classifier that's going to work well regardless of where we are using it, or in which kind of, let's say, time period we are using the kind of classifier. And then there is the idea of the invariant risk minimization. We can go into a bit of a detail, it's quite important. Now, what we are going to have, this actually does look quite a lot like the constraint-based supervised learning objective function that we talked about when we talked about the transfer learning and semi-supervised learning. I know that you don't remember, it's okay. It's okay. We're going to go through it again. So what is the idea? So the R is the risk or the loss. So that's the loss. But then this loss is going to be computed using the data set coming out of E, the particular environment. And then we are going to have many different environments that are used for training. So we now have a training set of environments. And then the goal here is to, of course, trying to find a classifier and feature extractor that works well across all the training environments, all of them, right? So that's why we're looking at the summation. And then what is this? This is the one that we have so where the W is going to be one of the classifiers that's going to solve the problem. So what we're doing is that we're trying to find a feature extractor that's going to work well. So we'll have one feature extractor that work well with one optimal classifier per environment. And then what happens is that once we have that one, this feature extractor, when we are testing it in a new environment, all we need is a few examples so that we get the classifier immediately on top of this feature extractor. Now what that means is this feature extractor extracts or that removes all the features that could induce some kind of spurious correlation between, that capture the spurious correlation between some of the original input variable and the output. So that's the goal of the invariant risk minimization. And then this actually turned out to connect very well with the idea of the meta learning as well. So in some sense, what is the goal of machine learning is for us to automate the process of solving a problem by using data where we don't know how to solve the problem. But then can we actually automate the entire process as well? So can we actually automate the process of machine learning? And that's the idea of meta learning, where we are going to be given a set of training tasks that we need to solve really, really well. So that in the test time, we're going to give a new task. And then the new task should be much more easy to solve. And then the test can be just translated into environments. So in this, let's go back to the invariant risk minimization. You can imagine that my training environments are the forest, cities, and then I can have a test environment that's going to be, let's say, seaside. Right? So if I actually get this feature extractor from an image so that this overall classifier is going to work really, really well for both indoors or the cities and forests, then one thing that this feature extractor is going to remove is the branches, because we know that the branches are not here. And then it's going to remove the cages. It's going to only keep the features that correspond to the actual birds. Right? And then given that feature extractor in the test environment, which is going to be seaside, in the seaside, that using the feature extractor doesn't know anything about the, let's say, sky or whatnot. So it's going to really just get us the shape of the bird. And then the classifier that we build on top of the feature is going to be invariant to the changes in the environments, and then thereby does not rely too much on spurious correlations. Now I'm saying that does not rely too much because again, we have the training environment, then there will be the test environment. What that means is that we have to somehow do some model selection ourselves to ensure that we choose the one classifier that's going to generalize not only across the training environments, but also to the test environment as well. Now, obviously, it's not easy for us to collect the data from the multiple environments. Sometimes we can do that. In the case of the image recognition, we could, in fact, spend some time and money in order to collect the data from the different cities and the market. So which city or which country all those images come from. But in general, it's not that easy. It's not that easy, not only because it's expensive or difficult to collect the data, but because sometimes due to the various reasons such as privacy, you may not be able to have those environmental information that allows us to break the dependence on the unobserved confounders. Turns out that there is a kind of a performance version of it, and that is called data augmentation. Especially in image processing is quite popular, is that because you want your classifier to be able to be robust to a bit of a shift or the rotations or whatnot, or the changing of the lighting conditions. So people have been using this kind of data augmentation over and over, but it turned out some of these data augmentation techniques turned out to create all those different environments automatically. Now, why is that? Because one of the things that in the case of the images, and in the case of the images, one of the things that tell us about one of the things that is the unobserved confounder is how the camera was configured. How the camera was configured is actually one such thing. And then if you think about this kind of branch detectors, one thing you notice is that the branches are almost always at the bottom of the image. So then if you do the data augmentation, that is by UID shifting up, shifting down, cropping here and there, what happens is that we're creating a lot of, let's say, different versions. And in some of them, these some spurious correlations will just disappear. Like if you do the cropping, then the branches tend to disappear. So this is a bit of a limited way to intervene on the camera configuration in order to mimic this kind of environment, invariance to the environment. Now, unfortunately, this only works for a certain domain for which we know how to do the data augmentation. In the case of natural language processing, how to do data augmentation itself is a very actively studied area because we don't know how to do that. Why don't we know how to do that? Because there is no inherent notion of distances. So we need to know what are similar to which ones are similar and then which ones are dissimilar in order to do the data augmentation. We're going to always perturb it so that it's going to stay similar. So how do we do that with the natural language? We don't know how to do that. So that's an actively studied area. But this is what people are doing. It's still quite limited, unfortunately. And here, we need to think about it a bit. Is that we often try to solve the problem using machine learning by assuming that what we have as a data is the whole thing that we can use in order to solve the problem, but it's almost never the case. And then there are always going to be things that we cannot collect data for, or sometimes we have to even throw away. So if you're going to solve the problem for problem in healthcare, we often can't really keep all those identity preserving information. Then you have to removing them actually does create all those as unobserved confounders there. So it can happen not only because of our inability or our inability to collect the data, but sometimes we're forced to do so. And then that means that we have to be very careful in using these machine learning algorithms that are often based on statistics in order to solve the problem, because you might actually end up with a classifier that does something that is completely unreasonable. So we need some way to do that. We talk about two things. One is that, okay, let's have a humans that in the system, once it's deployed, so that the human can actually create all those examples that are going to break spurious correlations for us. Unfortunately, that has a bit of an issue. We looked at it, like the people actually suffer from that process. And then if you're in, let's say, some rural Arizona, there aren't too many jobs. Then you get a job at Facebook, you're very happy, you go there, and then what you do is that you're going to see 24-hour, let's say, suicide notes posted on Facebook. Not really great. So then, is there another way that actually does not involve, let's say, torturing human beings? Turned out that the invariant risk minimization is one particularly interesting idea that can be pursued, although it is still limited, and then the applicability has not been tested well enough. So still in its infancy, and then this is the thing that you need to keep in your mind always when you build this kind of system, is that what is my system doing? Is the system actually doing what I want it to do? And if it doesn't, which is almost always the case, why does it not? What are the information that is missing so they cannot solve the problem in a way that I want it to? All right, so the third topic, feedback looping machine learning. And then we're going to talk about the two different things here, data contamination and exploration. Now, what do I mean by that is that what we think about when it comes to building a machine learning system starts from the data collection. Although we rarely even collect our own data because people collect the data, we're going to just download it from the internet. Train a model and then test it, right? Then based on the evaluation results, we're going to try to improve the learning algorithm as well as the data collection procedure. Not always, sometimes. But in reality, the true story is that we go through this loop and then eventually we're going to deploy the system. We are going to deploy the system, and then that deployed system affects the data collection. And then that actually creates a really weird feedback loop that can be vicious. And we're going to go through why it can be vicious. So Google Cloud Vision API, I don't know if you have tried it yourself, very easy to try. Just go there, you can upload your pictures, and then you see that it works amazingly well. This is just a picture from the poster session one of my friends took of me. It was detecting every single person you can imagine. And this is the picture that I took from Midtown, that's the Apple store. And then, oh my God, if you look at this is like perfect. It's getting me everything that I wanted to know. It even knows that it's the daytime. It's pretty crazy, right? of course, the daytime is a bit of a mistake, could be a mistake, right? In New York City, there will be a daytime, but let's say you're in Finland and it's June. Could very well be like midnight and it's going to look just like that. So again, if you imagine that this classifier was used in Finland in the summertime, this one is failing at the daytime prediction, right? But it works beautifully in general. But then you start wondering, okay, what was the data set that was used to train this system? And then you go into the ImageNet homepage and you can actually read about how they actually collected the data. Let's read it together. So ImageNet was constructed in 2009 through internet search and crowdsourcing. The research team obtained the vocabularies from WordNet. And then for each sense set in the WordNet, the ImageNet team in 2009 automatically downloaded images by querying search engines, one of which is definitely Google, right? And then they hired workers on Amazon Mechanical Turk to verify whether each image correctly depicts the synthesis of the word that they were searching for. Okay, so ImageNet was created using Google image search. They started from the dictionary, they searched the Google, and then collected the image. And then they built a convolutional network, which can detect all those crazy objects with a beautiful accuracy. And then Google Cloud Vision provides a service to the third parties of this convolutional network that was trained using the Google image. And then for these third-party users are the website providers. If you have, let's say, let's say you're eBay, you can use a Google Cloud Vision API to make sure that the product pictures are uploaded by the third-party sellers are actual product pictures. You can check them, and then you can tag them. And then if you're a Twitter, you're going to automatically create an alt text for images so that the people who can't see can still read about what is in the picture or hear about them. So they use it. So they use Google Cloud Vision for various purposes, including tagging. So that's the point. They're going to use it to show what kind of objects are in the image. But then you realize that where do images from the Google image search come from? From the internet that people upload. So there is this loop, right? So Google image search was used to build an image network database that was used to build a convolutional network that powers the Google Vision API. So people use Google Vision API to automatically tag all those objects in an image that they upload on the internet that are being used by Google image search to go into the data set that is used to build a convolutional network that's going to power the Google Cloud Vision. And then they are going to use the Google Cloud Vision. And it's a vicious loop. There are two issues. One is a selection bias. Essentially, for the images for which the Google Cloud Vision already works well, will get, or the objects that this Cloud Vision works well, will get better tags in this process so that they are collected better. So queried better in the Google image search, and then you get more images like that, and it gets better. But if your Google Cloud Vision was poor at a particular set of objects, that's going to get worse and worse. Because it's going to make a mistake. The mistake is going to go into the image data set and then you have to go. Second one is the error feedback. Is that if there was any error in the middle of this process, then that error is going to propagate to the next stage, sometimes often amplified. So it becomes pretty much a weird process where everyone is relying on an automated system that were created by the use of the automated system. That was created by the automated system. That was created by us. So this one is a bit of an issue, but then let's go to what we have learned about machine translation. Google Translate machine translation hasn't gotten so much better over the past 20 years, well, 18 years. So this is a blue score. This is a language pairs. And then this is sorted according to how well Google Translate works as of 2020. Now it covers about 100 languages. And then the blue score has just gone up like dramatic. It works amazingly. That's good. But then, of course, because it started to work really well, new problems started to appear. And then let's imagine where Google actually gets the data in order to train their machine translation system. It turned out they actually crawl the web. That's what they do, right? They crawl the web in order to create the data for machine translation system by having some kind of heuristic algorithm that mines all those parallel documents. Because in many parts of the world, they actually have to often provide the websites in multiple languages. For instance, in EU, if you're in the EU government, all the critical documents need to be translated into 26 or 27 EU official languages. If you are in Canada, then every government documents as well as any kind of official documents must be provided in both English and French. And then if you are in other parts of the countries, this happens over and over. And then you look at the newspapers. Those, let's say, cross-border, let's say, news agencies like the PAP, what they do, they're going to provide the same news article in multiple languages. So as to provide them to the local newspapers or the country, let's say, national newspapers. So those are the documents that are being mined in order to build a machine translation system used by Google Translate. In 2011 already, they noticed that this was they were hitting the limitation because they did some study very carefully. And then it turned out, for instance, in the case of the Tagalog, which is used in Philippines, I guess, yeah, I think so, yes. More than half of the documents that they actually crawled that were written in Tagalog were actually Google Translate. 44.5% of the Hindi content on the web that Google has crawled turned out also to be Google Translate. 42% of Galician content pages were also Google translated. And then you can imagine that if the machine translations is not perfect, but then we're using them over and over, again, we go into a vicious cycle. Now, what can we do? Do we just give up? We can't really give up, right? We can't really give up. So what can we do about it? How do we break this vicious cycle? It turned out that there is an algorithmic or the statistical method to avoid this, or to alleviate a bit of this issue. And that is called statistical watermark. So the user is going to read something on the internet or discover some text on the internet. And then this user doesn't know the language in which that content was written. Is going to send the text to Google Translate. But when the Google Translate returns the translated version of it, it's going to add some watermark. So that later on, we can check statistically whether the text was Google translated or not. And then based on that one, Google Translate can avoid using that particular translation as a training example, which can be detrimental. How do we do that, right? Because it's not like an image, right? So I don't know if no one is flying these days, but anyway, so when you used to travel, when you watch some of the movies on a plane, you see that once in a while you'll see the AF in short for Air France, or let's say Delta. Those are the watermarks, right? So because they want to figure out which of the airline actually leaked the movies, right? So they marked it like that. That's possible in images or the movies. In the case of the text, what can we do? It turned out, I'm not going to talk about the algorithm here because that algorithm is a bit outdated and better nowadays, is that you can now tweak the choice of words as you generate the text so that you can make those n-gram statistics to be slightly different from the n-gram statistics of the naturally created text. And then you can now run the statistical testing every time you have a text, some text given, to see if the n-gram statistics is closer to this tweaked generated text or the natural text. So you now have a probabilistic way to tell how likely this text was created by the Google Translate or not. And then using that turned out to work well, except that you suffer on the quality because you tweak the choice of the word as you generate, the fluency often goes down, although the meaning or the accuracy stays same. But it turned out we could do that. We could do that. And yes.
Does this leak into reality?
Sorry?
Does it leak into real life?
What do you mean leak?
Like the statistical and then changing?
Yeah, so that's an interesting question is that if we start doing this and then people start reading all this Google Translate text, is it possible that people started to actually write like Google Translate so that this statistical testing, the power actually goes down? That can happen, but the thing is, it's very subtle change. The one thing that Google or the Facebook can do, I'm going to talk about it a bit later, is that they have a advantage of scale, benefit of scale. So the statistical testing they can do have a huge power, even if the difference is extremely subtle for even people to notice. So they have this benefit of scale, which allows them to not really influence how people talk. To a certain degree, but you're right. So that this one has to be updated over time. But more serious possibility is that if you just push it a bit further, this actually means that you can actually track who said what without using anything other than just the text alone. And then this actually goes to the problem of the so-called auto attribution, which is an important problem, in particular for the historical documents and so on, because we do have a lot of historical documents that we don't know who wrote. But for the purpose of, let's say, historical studies and whatnot, we want to know. So that's very important. But that if you turn it around, that means that you can't really be anonymous when you write something nowadays. And then these services might actually be able to add in this statistical watermarking, right? Given, let's say you wrote a long blog post anonymously. You thought you were doing it anonymously. But when you upload it, the system might actually alter the text just a little, right? You won't even notice. But then when you look at it, let's say some kind of n-gram statistics or some kind of statistics, you can actually tell whether that was written by you or any other person. Then it's a bit of a dilemma we run into. It's like the browser cookie embedded in the text. And that one we can't really remove. Browser cookie, I think even removing browser cookies is becoming a bit of a ridiculous, let's say, issue these days. The browsers are asking you to click way too many times to remove them. But if it's a cookie that is embedded in the text, can't even remove. And then now this kind of, let's say, feedback loop is really getting serious, but there are some technical solutions. So we're going to talk about one technical solution. But before that, I don't know how often you notice, but these Google News and all these news services are extremely personalized. And then even if you're using all those in private browsing or whatnot, because of the location, it's going to be extremely, extremely personalized still for you. And even if you use VPNs, because the users of the VPNs tend to be similar people or the similar services, still personalized. So everything is super personalized. Let's look at these three things. So one of them is from my laptop 2020. Another one is from my friend laptop who lives in New York City, taken on the same day. And then another one is from a incognito mode using Google Chrome browser from my friend who lives in California. Again, screenshot it at the same time. Now let's see. Can you actually see the difference, right? So okay, let's look at the left one. The first one is that Biden says there shouldn't be a second debate if Trump still has COVID-19. That was the first one. The second one also has the same thing. Okay, third one also has the same thing. So far, so good. Now let's look at the second one in the list. White House event for families of deceased U.S. troops thrust into new light after MERS coronavirus diagnosis. Second column, we see essentially the same thing. But the third one, suddenly we see that, okay, oh, COVID, White House 8 test positive as military leaders quarantine. All right, it has changed. Let's look at the third one. The third one talks about essentially the same thing as the second one. Now, when I go to the second column, the third one actually is different from the first column. Trump rewrites the Russia probe from the hospital. And then the third column actually does change as well. So these are extremely personalized. And then I actually don't recall which one was mine actually. Can you tell? I think I can. Well, yeah, you see that these are the three different people, but all my friends living in 2 different cities, using different browsers, you get to see different news. Right? You get to see really different set of news. Then here's another example. And then the funny thing is that this one is just a headline, right? This is just headline. It doesn't even say it's personal. It doesn't say it's personal. And then now if you go scroll down a bit on Google News, then you actually do see that the section that says that, okay, it is actually for you. Although it turned out that this one was also for me as well, right? But this is for me. Now, can you guess which one is me here? I guess you can guess, right? Yeah. And then this was actually from the same room. I was preparing my slide, and then these are the, if I recall correctly, one of them was incognito mode, and then the other one was just my browser where I was looking. So you see the major difference between these two things. And then the difficult part about this kind of recommendation is, so it's now, we're looking at a very microcycle of the feedback, right? Before we were talking about, let's collect a bunch of data, let's to build a system, deploy it, and then that's going to change the data. But now we're talking about the very micro loop here, is that we need, all these systems these days are recommending us what to read, what to watch. And this is a necessary component of this internet era, just because the amount of information that is being produced is way more than anyone can actually take control of the editorial and then give us the, say, the right, common right set of articles or the things to watch. So there has to be some level of recommendation. But then what we notice is that the supervised learning did not work. So what people really, a lot of people did in 2004 and 5 was that they look at the article, right? Get the n-grams, extract n-grams, given them one, trying to predict the click-through rate. That is that how many users clicked it, right? When they were shown it, especially Google was using that one. And then that one was really important because you want to show we thought that we want to show the users the article or the web pages that they are likely to click and stay. I mean, it's often like 2 to 3 seconds, but then you click and stay. But then it was actually a bit of an issue because this classifier would only work well on already recommended articles. So when we try to make a recommendation, what we want to make a recommendation is based on the future, right? Based on what that person is going to like. But this kind of supervised learning is actually looking back, looking at the past and then trying to figure out what this person actually liked. Now, what this person liked versus what this person will like is 2 different things, right? But it's kind of, let's say, difficult to tell. And then because of that, for instance, if I had only recommended and read AI-related articles to a certain, at some point, then how would a classifier ever know that I would actually click and read the article about, let's say, new executive order on H-1B? Very unlikely that the system will know, right? So what that means is that the system, any good recommendation system must explore. It cannot just exploit the information that is at our hand. It has to explore. In other words, it needs to actually give us some random things and then figure out if the user liked some of those random things that even the user didn't know they liked. And then that can inform us about what are the things that user may like in the future. As you can get, it can be detrimental in short run. Right? Because if my recommendation system suddenly tells me that well, why don't you, they're trying to watch this, the documentary about the Asian Greeks. I'll be like, no way, man. No, I'm not going to watch it. I don't like it, right? But then in long term, it's going to know that okay, so the historical documentary about Asian Greece or the Asian, let's say, the Mediterranean area, probably no. We're going to show them something else. So it can be beneficial in a longer term. And in 2010, the group at Yahoo back then posed an idea called contextual benefits. The idea is that there are going to be always these news articles from, let's say, today. Now I need to decide which one I'm going to show to a user. Then what should I do? What I'm going to do is I want to maximize the reward over time. So I'm going to make a decision to show one article at a time. And then I don't really care if the user clicked that article now, right? That's too instantaneous. I want a longer term reward. On average, over time, what is the number of the clicked and read articles the user has matters. So even if I gave the user a good article now, so that the user clicked it and read it, if I fail in the future a lot, doesn't happen. It's better if I fail initially, but then based on the failed experiment, I learned so that I can actually maximize the click-through, a chance of the click in the future. That's even better. So what you do is that you explore. So you're going to toss a coin. If it lands head, you're going to say, oh, there's some random article. Take a look. If it lands tail, you're going to say, well, I know what you like. You like to read about politics. So here's a politics related article. And then you just do this randomly. And then by doing this kind of random exploration, you get better and better at figuring out the preferences of the user. And that's the idea behind the contextual bandit. Now, the very nice thing about this contextual bandit, which is for online learning, is that it has a very strong theoretical guarantees. In fact, what we are now going to look at is not the accuracy. We're not looking at the accuracy because every single example is correlated. Right? So the decision that I make is going to influence what I'm going to show. So why is that? Because if I decided to explore a lot more, then based on the exploration, I'm going to change. The classifier is going to adapt itself so that what it's going to propose next time for the users click or not changes. So we don't look at the accuracy anymore in this online learning setting. In this online setting, we look at the so-called regret. That is that if I had access to all those data sets, all those data points, right? And then retrospectively, what would have been the optimal classifier I could have built? Now, I have that optimal classifier. And then now, second one is where I actually really just make a decision as I go along. Okay, here's a new, they're scrolling. User has scrolled a bit down. I need to give the user the next post to read. Now, what can I do? I make the best choice I make. Now, the gap between this best choice I make, given what I have seen so far, versus the best choice I could have made, had I had access to the entire history, so into the future. So that's and then we sum them up, that's called regret. So that's a regret. So it's like literally the word regret is that if only if I knew that this was going to happen, I would have done this rather than this. And then the gap is the regret. So we look at the regret, and then we actually have a theoretical guarantee under some strong condition that we can bound the regret by the square root of the number of steps. So the regret, so the error I make against the potential, the hindsight optimal decision does not grow, does not accumulate as we go forward. We can actually do better than. We're going to reduce the regret over time. Quite nicely. So that's a very strong theoretical guarantee, but it's not really enough in practice. There are just too many candidate articles from which we choose, and then unfortunately there is a K, that is the number of the candidate articles. And then if you think about the news article these days every day, we have hundreds of thousands of new articles that are being written down every day. K is too large. The regret is going to be gigantic just because there are so many options from which we can choose. And then furthermore, the user's preferences change way too fast. So here, this guarantee actually does not tell us anything about how it actually assumes that the user's preference stays more or less same. It's not adversarial scenario. You can make an adversarial scenario in which case this one is going to get worse. But in reality, users' preferences change. I don't know if you notice, this is the idea behind the slightly ill-defined concept of the filter bubble. Is that you get to see something, and then you tend to believe that there is a majority view of the world, and then you tend to, let's say, sympathize with it. Then you see more of them because you tend to read more of those articles and so on. So users' preference actually, so we are much better learning algorithm than any machine learning algorithm, meaning that we are going to that so much faster. So that's a bit of an issue. So exploration often cannot catch up with the rapid drift of the user's preference as well as the article's topics as well. And then the word is so non-stationary, right? Word is so non-stationary. So then what can we do? It turned out that this scale, the benefit of scale applies here as well. So this is the number of users. So in this Facebook, I think that this one actually includes the Instagram as well. So on Facebook, as of 2020, so Facebook / Instagram, there are like 2.2 billion monthly active users. On Qzone, which is no one uses anymore, let's say on Weibo, there were about 500 million monthly active users. Twitter had about 250 million monthly active users, and on and on. And then these numbers are only going up. These numbers are only going up. What that means is that we now have, if you recall, what was the issue with the randomized controlled trial? Is that it's not easy to randomly assign group of positive number of users to the all possible configuration. But if you have 2.5 billion active users, you can actually do a lot of things simultaneously. And then there is so-called A/B testing. And then I would like to call it at a massive scale. And then it turned out that by doing so, you can actually learn a lot about users as well as the society. In 2014, Kramer, Guillory, and Hancock back then at Facebook conducted the A/B testing on Facebook to test the impact of the emotions or the emotional post on the user behavior. And then in particular, user behavior as in how engaging they are, which is measured by a proxy, that is how often they come back to the Facebook page. And then they ran an experiment with the 700,000 users for about a week. Now, if you think about how many people we enrolled in order to get the vaccination, the phase 3 of the clinical trial done, we had about 30,000 people. And then there was, let's say, the people we enrolled from the multiple countries at a time almost all. Here, with a click, like, all right, we need 1 million users being tested on. It just happens, right? And then what they did was that they built a system that's going to detect the emotion of a post, and then they dropped each emotional post with a probability between 10 and 90% of chance from newsfeed for half of the users, right? About half a million of them. And then this is how they define it, and then they observed that okay, there is something called emotional contagion. Emotions expressed by friends via online social networks influence our own mood. So until then, this was a more or less a hypothesis, but they actually confirmed it. And the second thing is the so-called withdrawal effect. So people exposed to fewer emotional posts were less expressive on the following days. Less expressive as in they haven't actually posted too much on Facebook. Now, okay, they didn't do anything. They didn't do anything with this. They just wrote a paper. They were criticized quite heavily back then. But then hypothetically, let's say you are a decision maker, or let's say you're Mark Zuckerberg, and you read this paper. What would you do?
You would increase emotional posts.
Well, I mean, hypothetically, that would make actually the shareholders happier in general, right? Yes. And then there is that actually raises a question. Exploration is necessary for us to be able to break this feedback loop that is negative, right? This vicious feedback loop can be broken down if we intervene by exploration. But what kind of exploration can we allow? When you deploy this kind of recommendation system, you will have to explore. That's like, you have to, it's impossible not to. But then what kind of exploration are you going to allow yourself to have? That's it. Anyway, still, if you do some kind of exploration, change the environments, all those things, there are some technical solutions that we can start from. But there are some cases where we can change the environments easily, we can explore, nor we cannot experiment. And one of those cases is hiring. You can't explore in making hiring decisions. You can't say that, I need to hire a CEO of the company, but this time I tossed a coin and it landed heads. So I'm going to actually randomly choose a random person on the street and then hire that person as a CEO. We can't really do that, right? That's a bit too risky, right? And then we can't really rely on then machine learning algorithms because these algorithms cannot explore. Because it cannot explore, it won't be able to actually break this feedback loop that is, and then it's going to rely on the spurious correlation and it cannot really remove that reliance on the spurious correlation. And then in fact, Amazon, as well as a few other companies, and then in fact, many companies, increasingly more companies these days are testing all these AI-based recruiting, in particular on the decision-making side of the filtering candidates early on. And then that actually turned out to be a pretty bad idea for many reasons. But one is that, okay, we cannot rely on it unless we let these algorithms have an ability to explore, experiment, or provided with the many different alternative environments and making sure that these algorithms work well invariant to the change in the environments, but all of which turned out to be impossible. So this kind of scenario. So this what this tells us is that when you're trying to solve a problem, the first thing that you need to do, actually second thing, I'm going to talk about the first thing in the next slide. Second thing you need to do is whether the problem actually can be solved with your current technology. If you cannot, then there are two ways forward. One is that, okay, you're going to actually work on coming up with new technology in order to solve that problem, or you have to figure out how to change the problem. You cannot just try to solve the problem with the current technology while you know that it's not going to work and hope that it's going to work. You can get lucky, but generally that's not really so you cannot rely on luck when you do the engineering and science. That's the worst possible way to do engineering science. So there is this kind of vicious cycle. It's a bit difficult to break. There are some, let's say, technical solutions that are still in their infancy in general, but that's how we kind of progress. So we need to know about what is the problem in order to solve. So finally, because you all are going to, I'm going to skip this because I'm running out of time. So because you're all going to become some, let's say, engineer or decision maker who's going to build a product, and then you're going to deploy those products, and then billions of people are going to use it directly or indirectly. So then the most important thing is to be able to imagine the consequences of what you build and deploy. And then these consequences can not only be positive consequences. When you talk to, let's say, venture capitals or trying to pitch your idea to them and then trying to raise funds, you always talk about the positive consequences. And then there is a reason why we have a tendency, especially among the engineers, to think of the positive consequences more so, but we also need to be able to imagine all these negative consequences. So you go to the Instagram.com, and then if you don't log in, and you're going to see all those amazing things that Instagram has done. There are like more than 100 million pictures and videos uploaded every day to Instagram. And the number of the monthly active Instagram user as of last year, even pre-pandemic, was more than 8 billion. And then they say that Instagram is great, we're bringing you closer to the people and things you love. You can express yourself in new ways with the latest Instagram features. All those things. And it makes sense. Why are they doing that? Because there is if you imagine the positive consequence of this social media, it's actually awesome, right? So we want if we bring the users to the platform, so that users can engage with the platform with each other, then they're going to be able to have a more social contact with the other users. And then more humans are social. So they're going to be more happy. They're going to be happier. And then happier people, better society. Thereby, we're going to maximize the growth of the user base and engagement level of the user, measured by how many pictures they upload, how many likes they get, how many hours they spend, and so on and on. Now, you probably have followed on those so-called Facebook papers or not in the recent years, or recent month, actually weeks. It's already actually, it was from the 2017 or 18, the Royal Society for Public Health did a survey of the teenagers in UK on their use of social media and how they feel about it. And Instagram was, of course, one of them. They asked them, has the awareness of yourself grown since you started using Instagram? Are you getting more emotional support than before? How's your anxiety level? Do you sleep better nowadays? How do you think about your own body's image? Is it helping you build a community, or has it helped you with the bullying issues and whatnot? Now, it turned out that it's largely negative. The Instagram was supposed to connect people, make people more social, so that they become happier, and then the society is going to be better. Then it turned out it's actually not that great. It's not really that great. So why is that? Why is that? Why is that? I think, because they couldn't really imagine the negative consequences of their system, potential negative consequences. The founders of Instagram, and then much of the developers who are developing Instagram, they don't know how teenage girls think. And they couldn't imagine the negative consequences they would have on teenage girls who are like literally, some of them are literally starving themselves to death, but because to get the higher likes, right? So yeah, so it's really important to imagine both positive and negative consequences. And then to do that, you have to be, and then you now can do it because you know the technology behind it. You know all those algorithms, you know how the algorithms don't work well, and how they work well as well. So trying to do that. I can skip this one. And that's it for this lecture. And then, well, that means that I'm done with lectures myself. We're going to have the guest lectures, but that's it. That's for the guests to do. I'm going to now work on preparing the final exam. And enjoy the Thanksgiving off next week, and I'll see you in 2 weeks then.